All right, for you sports fans out there, we're going to take a look at a little bit of football data. So this is from the 2023 NFL season, and what we've got is each team, how many wins they had that season. That's what we've got in column B right here. And then in column C, what we have is points for, that's how many total points that team scored that season. So in other words, it's showing their offense. Uh, Column D is points against. That's how many points their opponents scored against them. So that's measuring their defense. And then this column E, is points differential. For those of you who don't know what that means, in math, difference means subtract, right? So this is simply taking the points for and subtracting points against. So for example, for Buffalo, 451 minus 311 equals 140. So that means that they scored 140 points more than their opponents did that season. Miami, if you do 496 minus 391, you get 105. Why did the New York Jets? How come their point differential is negative? It's because their opponents scored more points against them than they scored. So if you do 268 minus 355, you get negative 87, right? So you want your point differential to be positive. So what we're going to do is we want to consider, is there a correlation? And remember, correlation means a mathematical relationship between two things. Is there a relationship between the number of wins that a team gets and how many points they score? Also, is there a correlation between the number of wins and the points against? And then lastly, is there a correlation between the number of wins and the point differential? So what we're going to do is we're going to take all this data, I'm going to copy it, I'm going to paste it into my Desmos screen right here, and there's all the data. Just so you understand what we're looking at, the x-axis represents the number of wins that the team had, and we're going to compare the wins to all three of those different things. How many points they scored, how many points were scored against them, and their point differential. So let's just look at these one at a time so that it's not so overwhelming. I'm going to get rid of, so you guys know, X represents the number of wins. Y is the points scored. How many points? That's their offense. Z is the number of points against, so that's the defense. And then U, this represents the point differentials. Let's just look at the first thing. Let's just look at just the points for. And so let's consider, does there appear to be a correlation here between wins and points for? Yeah, there does. You can see that there's clearly a positive correlation between these two things, right? Let's look at just the defense. So we'll just look at Z1, and you can see that there is a correlation between the points against and the wins. What do you think? Is this a positive or a negative correlation? And why? This should be a negative correlation. Remember, negative correlation means that as you get more wins, you can see the points are going down. And the reason for that is, that makes sense, right? That the more wins you get, typically the less points you're going to allow. What about point differential? Is there a correlation there? So let's look at the U1 table. And what do you think? This looks like definitely a positive correlation between wins and point differential, meaning the more wins you get, the higher your point differential ought to be. So here's the next thing. One really amazing thing we can do with Desmos is we can actually ask Desmos to make a function that is the best fit equation for our data. So let's go back and look at offense for 1 second here. Here's the scatter plot for wins with points for. If you notice right over here, there's this little icon. It says add regression. That's what we're working on in this unit. Regression simply means taking data and matching it with a function that models the data well. That's exactly what we want to ask Desmos to do. Desmos, can you make for us a line that follows that data as well as possible? So if I just click this button right here, that's exactly what it does. It's going to make a line that's as best as possible following the data. Let's take a look at what we got here. If you remember from Algebra 1, the equation of a line is y equals mx plus b. This is the equation of the line that we got right here, right? Remember from Algebra 1, that first number is the slope of the line. and the number at the end is the y-intercept, 184. You can actually see that's exactly what the y-intercept is for this line, right? So also remember last lesson we looked at r squared. R squared tells you how good of a fit that is for the data. You can see it's almost 0.7. So that's a fairly good fit for the data, right? Okay, we can do the exact same thing for the other data plots. So let's look at next defense. I'm going to switch this off for a second. Let's switch over to the second column. This is points against. And if I simply switch from y1, which represented the points for, to z1, now Desmos is going to come up with a new equation for me that represents the best fit function for points against. Notice the slope of this function is negative. That's because it's a negative correlation. Notice also the r squared value. This is very interesting. It's only 0.35. So last season in 2023, it looks like there was a stronger correlation between offense and wins than there was between defense and wins, which is kind of interesting. I wouldn't necessarily have expected that. All right, lastly, let's do the same thing for point differential. So we'll switch over to U1. And I'm going to switch my regression, my linear regression. Remember, linear just means it's a line that we're looking at from Z1 to U1. And there's my line of best fit for that data. Look at the r squared value this time, 0.8. This is the best fit. And actually, that makes a lot of sense, right? Because if you think about it, if a team's got a really good offense, they might still not get a lot of wins if their defense is bad, right? So even though there's definitely a correlation between offense and wins, it's not as strong as it could be because it doesn't factor in the defense. Likewise, there's definitely a correlation between your defenses, how strong your defense is, and your wins. But it's not going to be but so strong because if your offense is no good, you're still not going to win a lot. But point differential, remember what we said, that factors in both your offense and your defense. It's the points for minus the points against. So if you've got a really good point differential, that means you probably have a really good offense and a really good defense, right? So that's why this is the strongest correlation out of the three. And sports analysts will tell you that point differential is probably one of the single best predictors of how good a team is going to be. All right, so let's consider for a second here. Based off of the coefficient of determination, the r squared value, which was the strongest correlation out of these three? Which is the best, the most closely related with how many wins a team gets? And that was point differential. That's the most important predictor out of these three for how good the team is. Second was points for, the offense. And then the weakest correlation was the points against, the defense. Which one was negative? That was the points against, the defense, right? Because again, the more wins a team has, the less points they're going to allow against them. All right, let's look at one more thing here. It says write the line of best fit equation for point differential. So let's just get that equation and take a look at it for a second here. So here's my linear regression, my line of best fit for point differential. I can actually copy this very easily just by simply clicking this button right here. Export a snapshot. And here is my line of best fit for point differential. So I'm just going to copy that. I'm going to paste that right here. There's my line of best fit for point differential. This function gives me the relationship between the number of wins a team has and their point differential. It says use this equation to predict the point differential for your favorite team based on their number of wins last season. Well, I'm going to be honest. My favorite team is the New York Giants. And so I'm going to go back and see how many wins did they have in 2023? They had a whopping 6 wins. So remember how this works is X represents the number of wins that you had. So I'm going to go back to my equation over here. And what I want to do is I want to use my function to predict if my team had 6 wins, what would we expect their point differential to be? There's 2 very easy ways to do this. One way is I can just use my graph. I can just, remember, X is the number of wins. So I can click on my graph, click and hold, and just drag it until the X value is 6, because that's how many wins the Giants had. And the prediction is that if the Giants had 6 wins, they would probably only have a point differential of about negative 81. Negative, again, means that they're giving up more points than they're scoring, right? The other way I could do it is I could take my function right here and replace X with the number of wins that they had, which was 6. And so this function is going to follow the rule. It's going to do 6 times this number minus this number, and it's going to predict the number of, or the point differential. And again, we get the exact same answer here. You can try this with other teams and see, one of the amazing things about this is you can go beyond the data here. So there was no team that had 15 wins last season, right? Like the team with the most wins was 13. But the amazing thing, and this is the reason we learn about regression, is this allows us to go beyond the data that's given to us. We can predict what would happen if a team had 15 wins. We can use that to predict what the point differential would be for a team that had that many wins, right? We can go up to 16 or 17 wins and use this to predict what would you expect the point differential to be for those teams. All right, this example might not be quite as exciting, but very practical and useful in the real world. Let's consider the correlation between the square footage or the size of a house and its sales price. We can see that there clearly is a correlation. It's a positive correlation because the bigger the house, typically the higher the sales price. If we could predict what the R squared value would be, what do y'all think it might be? I wouldn't think it'd be over 0.9 because the correlation doesn't seem to be that strong, but it's clearly there, something positive here. So let's see, let's make the line of best fit. Let's do a linear regression for this data. Again, all you gotta do is press on this button right here, this icon. You can kind of see the little points with the line going through it. Click that button, and there's the line of best fit for the data. In this case, the slope right here, 87, that's telling you that typically you're getting 87, it's about $87 per square foot. That's what that number means. The R squared value is 0.6, so it's a decent correlation. It's not super strong, but it's clearly there. I can click this button to make the equation. This is my function for my line of best fit. We talked about how well it models the data. Let's predict the sales price for a 3,500 square foot house. Again, remember, this is the whole reason we really do this, right? It's interesting to come up with a line that models the data, but the real power in this is now we can make predictions, right? We can imagine you're in real estate or you're shopping for a house. What if we were looking at a house that's bigger than anything we have in this data set, right? We can extend out to 3,500 square feet and get a fairly accurate prediction of what that house would cost. So we could use our line, looking at the graph, try to get it back to 3,500. And you can see that the predicted sales price would be $299,805, right? The other way you could do that is you could just replace the X value with, remember, X is the square footage. So just replace X with 3,500 and it gives you the same answer, $299,805, right? So we'll put that in there. Last question here is predict the size of a house that costs $400,000. Now I want you to notice that this $400,000 right here, that's talking about the Y value, not the X value, right? X represents the square footage. Y represents the sales price. So now we're not going to plug 400,000 in right here because this, remember, that was our X value. So instead, what we're going to do, there's two ways you could do this. You could use the graph. You could find on the Y value, when is the Y value going to reach $400,000? So you can kind of move over here and just drag along the line until the Y value, the second number, reaches 400,000. And that's about It's hard to get it exact. It's about 4650 or so, roughly. If we want to get it a little bit more accurate, we can do just a little bit of algebra. Let's take this equation, and I want to know when will the y value equal 400,000. So I'm just going to replace that y value with 400,000. And Desmos is actually giving me the answer right here, right? It's going to be 4,650.5 square feet. But if we didn't have a computer, we could get this very easily just doing 2 steps. Remember back in Algebra 1, how do you get x by itself here? Well, the first thing you would do is you would add this number to the other side, right? So we're going to do 400,000 plus 4,993. So, and I'm just going to copy it so I don't have to retype it. That's going to give me 404,993 over here, right? So since we added that to both sides, now the last step is to divide both sides by this number to get x by itself, right? So we're going to do this divided by the $87 per square foot. And that gives you the exact same answer, 4,650 square feet. That's what you would expect to, the size house you would expect to be able to get for $400,000. Let's do one last example. Probably the least interesting example yet, but there is a correlation between how fast crickets chirp and the temperature outside. It looks like it's a positive correlation, which would mean that the faster they're chirping, the hotter it is outside, which I guess that makes sense. Let's make the line of best fit. Click on Add Regression. There's your line of best fit. I'm going to copy it. So it looks like they're chirping about 3 times per degree, roughly, a little bit more than that. The R-squared value is 0.7 almost, so it's a fairly decent fit. Not super high, but not bad. Predict the temperature when they're chirping 19 times per second. 19 chirps per second. Chirps per second is the x value. So you can, 2 ways you could do it. Follow the line to when the x value is 19. And the prediction is that it'd be about 87.8 degrees outside, right? Or the other way you could do it is you could just replace the x value with 19, and that gives you the predicted temperature as well, 87.8 degrees. Predict the temperature when there's 22 chirps per second. Just follow the line up to 22. Or if you prefer, you get almost 98 degrees. Just, again, plug into your function the number 22. Remember, this function is giving you the relationship between the temperature and the number of chirps. So if they're chirping 22 times per second, the function is going to predict what the temperature would be outside, 97.6 degrees. Finally, predict the number of chirps per second when it's 100 degrees outside. Notice this time 100 is not the x value. It's not the number of chirps, but that's the temperature. That's the y value, right? So this time, we're not going to plug 100 in for x into the equation. We're going to plug it in for y. So here's my original equation. The y value this time is going to be 100. And so you could follow the line and get your answer right there. It's going to be about 22.7 chirps per second. But let's just do the algebra real quick. Suppose we're on a desert island somewhere and we don't have Desmos, and we want to know how many chirps per second it would take for it to be 100 degrees outside for a cricket. How are we going to do that if we don't know how to do a little bit of algebra, right? So what do we do? 2 steps. First, subtract the 25 from the 100. Get 74.7 such and such. And then step 2, just divide both sides by the 3.29 chirps per second. And the prediction is 22.7 chirps per second. It would probably be about 100 degrees outside.